You are about to fall asleep to one of the most grounded what-if stories in all of science. 66 million years ago, the dinosaurs were wiped out by an asteroid, but scientists have calculated that if it had arrived minutes earlier, it would have missed the shallow water and the extinction never happens. Tonight, we follow that world. 66 million years ago, on an ordinary spring morning, a rock the size of a small city was already 20 seconds from ending the most successful rain in the history of life on Earth. It had been traveling for millions of years, its path shaped by Jupiter's gravity, nudged by passing comets, wobbling on its own axis across the darkness of space, with no destination, no intent, just mass and momentum, following the same physics that govern everything else in the universe. The dinosaurs below had no warning, no signal, no instinct that fired. One morning, the sky was clear, and then it wasn't. And then 75% of all species on Earth were gone. But here is where it gets strange. The asteroid did not have to hit where it hit. Researchers have run the calculations, and the result is uncomfortable in the way that only pure contingency can be. If the Chicxulub impactor had arrived just minutes earlier, or later in Earth's rotation, its trajectory would have carried it over deep ocean rather than the shallow, sulfur-packed coastal shelf of what is now Mexico. The energy of impact would have been the same. The shock wave would have been the same. But the sulfur, the specific ingredient that turned a regional catastrophe into a planet-wide extinction, would have stayed locked in the ocean floor rather than vaporizing into the upper atmosphere. The darkness that followed, the years of blocked sunlight, the 30-degree temperature collapse, the cascade that killed 3/4 of all species, none of it happens without that sulfur. And the sulfur was only there because of where the rock landed. Not why, just where. The asteroid hit shallow water. That is the entire story. The Chicxulub impactor struck a shallow coastal shelf packed with sulfur-rich sediment, and when it vaporized, it sent billions of tons of sulfur dioxide into the upper atmosphere, enough to block sunlight for years, enough to drop global temperatures by nearly 30 degrees Celsius. A deep ocean impact, the kind that would have happened if the asteroid arrived just minutes earlier or later in Earth's rotation, produces a different result entirely. Tsunamis? Yes. Fires across coastal regions? Yes. But not a sustained sulfur winter. Not 3/4 of all species gone. Scientists have run the simulations. The outcome is clear. The asteroid's destruction was not inevitable. It was geometrical, a matter of where the rock landed, not whether it fell. Everything that followed, every mammal, every primate, every human ever thought, traces back to that single variable, not intelligence, not natural superiority. Geometry. Before we can follow this alternate timeline forward, we need to stop and look at what was actually there. Because most people, when they imagine the world the dinosaurs would have inherited, are imagining the wrong world entirely. The late Cretaceous Earth is not the barren, unstable place that popular imagination tends to picture. What was alive on that planet 66 million years ago was stranger, more complete, and far more formidable than most people realize. And understanding it changes everything about what comes next. Before we can imagine what happens if the asteroid misses, we need to understand what world it almost didn't destroy, because the late Cretaceous Earth was not the dying, unstable place that textbooks sometimes imply. There were no ice caps. Sea levels sat 170 meters higher than today. with a warm inland sea splitting North America down the middle. Crocodilians lived above the Arctic Circle. Forests grew where Antarctic ice now exists. CO2 ran 4 times current concentrations. This was a greenhouse planet at full operation, and the animals living on it had been refining themselves for over 150 million years to fit it perfectly. But the picture gets more specific than that, and more unsettling for anyone who wants to believe dinosaurs were primitive animals coasting toward inevitable replacement. T-Rex was not a lumbering scavenger. Forward-facing eyes with visual acuity exceeding a modern hawk, packed into a skull attached to 9,000 kilograms of muscle, capable of locating prey from 6 kilometers away. This was a precision predator, not an accident of evolution. Triceratops wasn't a scattered, struggling species either. It made up 5 out of every 6 large dinosaur fossils recovered from late Cretaceous North America, which means the herds covering those plains weren't comparable to anything alive today. Picture the Great Plains bison migrations, then replace every bison with an armored, 9-ton animal whose horns could kill the apex predator of its ecosystem. But the most telling detail isn't the large dinosaurs. It's the small ones, the mammals, none larger than a badger, living in the shadows of animals that had owned the planet for 165 million years, surviving by staying completely out of the way. The late Cretaceous Earth was not a world in decline. That is a story we told ourselves afterward, a story that makes the extinction feel like inevitability rather than accident. The reality is that 66 million years ago, the planet was running at full capacity. No ice caps, sea levels, 170 meters higher than today, pole-to-pole forests, CO2, 4 times current concentrations. T-Rex had forward-facing eyes with visual acuity beyond a modern hawk, capable of locking onto prey from 6 kilometers away and weighing 9,000 kilograms of precision musculature. Triceratops made up 5 out of every 6 large dinosaur fossils in late Cretaceous North America, not scattered survivors, but the dominant megafauna of an entire continent, moving in herds that would have made the Great Plains bison migrations look modest. These animals were not struggling. They were not evolutionary dead ends waiting for replacement. They were the apex products of 165 million years of refinement, perfectly matched to a world that, without the asteroid, had no reason to stop being theirs. Now that we know what world the dinosaurs would have kept, the next question is harder. Why were they so dominant in the first place? The easy answer is that they were big and scary. But the real answer runs much deeper than that. It gets into biology, into physiology, into the specific machinery of the dinosaur body that made mammals fundamentally unable to compete, no matter how much time they were given. And the part that most people never hear is not about the dinosaurs at all. There is a story we tell about the dinosaurs, that they were already declining by the time the asteroid arrived, that mammals were quietly waiting in the wings, that the extinction was in some sense inevitable, maybe even overdue. It is a comfortable story. It makes the rise of mammals feel like progress rather than accident, makes human existence feel less contingent, less fragile. Dinosaurs reigned for 165 million years, 66 times longer than the entire genus Homo has existed. And at no point in that span did the fossil record suggest they were losing ground to the small, warm-blooded animals living in their shadows. But the biology is even more one-sided than the fossil record alone suggests. Dinosaurs breathed through a system that no mammal has ever evolved. unidirectional airflow moving continuously through rigid lungs connected to a network of air sacs distributed throughout the body, which is why modern birds can fly over Everest at altitudes where mammals cannot function at all. That respiratory system is also why sauropods reached 50 tons, while the largest land mammal in the entire history of mammals never broke. 20. The dinosaur body could scale in ways that mammalian physiology simply cannot sustain. Hollow, pneumatized bones gave dinosaur skeletons a strength-to-weight ratio no mammal skeleton can match. Egg-laying meant females didn't have to carry developing young through months of reduced mobility. But the most clarifying fact is not about dinosaurs at all. It is about why mammals were small, and it is not the answer most people expect. The mammals were waiting for their chance story is wrong, and the fossil record makes this clear. Early mammal ancestors were not being suppressed by dinosaurs and quietly biding their time for an opening. A 2021 study out of Oxford and Birmingham found they were being outcompeted by other mammals, multituberculates, Gondwanatheres, animals that had already claimed the small to medium ecological niches from the inside. Mammals were boxed in on multiple sides, not just from above. Meanwhile, dinosaurs breathed through a system no mammal has ever evolved. Unidirectional airflow through rigid lungs connected to air sacs distributed throughout the body. The same system that lets modern birds fly over Everest while mammals cannot breathe at base camp. That respiratory advantage is also why sauropods reached 50 tons while the largest land mammal in history never broke. 20. The dinosaurs didn't dominate because they got lucky early. They dominated because their biology was, in measurable, documentable ways, more efficient than anything mammals had yet produced. The extinction didn't reveal that mammals were better. It revealed that, given no catastrophe, they never would have gotten the chance to find out. The dinosaurs survive. The world continues. And for the first 10 million years, the changes are quiet, not dramatic, not sudden, but constant, and accumulating in the way that evolution always works, slowly, invisibly, until one day the animal that emerges from the forest looks nothing like the animal that entered it. Something is moving through the canopy of the alternate Eocene that would be unrecognizable to any paleontologist studying the Cretaceous. The question is what made it and how fast. The asteroid in our timeline reset the planet, but in the alternate one, the one where the rock hits deep ocean and the sulfur winter never comes, the Cretaceous world simply continues. The angiosperms, the flowering plants, were already mid-conquest when the asteroid almost arrived. They spread faster than ferns, reproduced faster than conifers, and had already developed a relationship with animals that no plant group before them had managed. They were paying animals to carry their seeds. Fruit was the payment. Sweet, calorie-dense, brightly colored flesh wrapped around a seed, a biological contract that had been running for millions of years before the near miss, and that accelerates dramatically after it. But the Maniraptorans were not generic dinosaurs waiting for something to eat. Dromaeosaurids, troodontids, and oviraptorosaurs already had grasping hands capable of closing around branches, forward-facing eyes that produced the depth perception needed to judge distances between tree limbs, and bodies light enough to move through canopies that would collapse under the weight of larger animals. They were already climbing before the asteroid almost arrived. The angiosperm forests give these lineages something they had never had in quite this form, a food source that rewards mobility color recognition, and the ability to reach into dense canopy rather than standing beneath it and waiting. But 10 million years of selection pressure in fruit-rich forest does not simply make a raptor better at eating fruit. It remakes the animal, shrinks the body toward the weight that canopy branches can support, curves the beak toward the geometry of tearing soft flesh from seeds, diversifies the feather coloration because in the canopy, color is information, and information determines who reproduces. Fruit changed the rules of the Cretaceous world before the asteroid ever arrived, and the Maniraptorans were already positioned to exploit it. Grasping hands, forward-facing eyes, bodies small enough to move through canopies, the dromaeosaurids and troodontids were not waiting to evolve into something useful. They were already climbing. In the 10 million years following the non-extinction, the angiosperm forests would have continued their spread across the continents, and the dinosaurs moving through them would have followed the food. A lineage descending from oviraptors, given 10 million years of selection pressure in dense, fruit-rich forest, would not look like the animal it started as. The body shrinks, the beak curves, the color diversifies. Because in fruit-eating canopy animals, color matters for signaling, for mate selection, for group recognition. What emerges is not a bird and not a raptor, but something that fills the ecological space currently occupied by howler monkeys and spider monkeys, a feathered canopy animal with grasping feet and a hooked beak, moving through a world of flowering trees that had no reason to stop growing. 10 million years into the alternate timeline, the dinosaurs have settled into the angiosperm forests, diversified, spread, things are going well, and then the planet tries to cook them. Roughly 55 million years ago, global temperatures spike by 8 degrees Celsius in less than 20,000 years, one of the most dramatic warming events in Earth's history. In our timeline, this event reshuffled mammalian evolution so completely that it's where primates first appear in the fossil record. In the dinosaur timeline, the same heat arrives. The question is whether the dinosaurs were built to survive it, and the answer is not what you would expect. Roughly 55 million years into the alternate timeline, the planet runs into a problem that has nothing to do with asteroids. Deep ocean sediments begin releasing carbon, possibly from volcanic activity, possibly from methane hydrates destabilizing on the ocean floor. The exact trigger still debated, and within roughly 20,000 years, global temperatures spike between 5 and 8 degrees Celsius. Palm trees push into Alaska. Crocodilians bask on Arctic shores. The event is called the Paleocene-Eocene thermal maximum, and in our timeline, it reshapes mammalian evolution so completely that the first primates appear in the fossil record exactly at this boundary. In the dinosaur timeline, the same heat spike arrives, and it finds a world still ruled by animals built for warmth. But the heat spike does not affect all animals equally, and this is where the dinosaur timeline diverges from ours in a way that changes the trajectory of everything that follows. Small, fast metabolizing mammals generate body heat quickly and lose it quickly, which makes rapid temperature changes genuinely dangerous, forcing physiological stress responses that larger animals with thermal inertia simply do not experience at the same intensity. A large dinosaur absorbs heat slowly and releases it slowly, buffered by sheer mass against the kind of temperature swings that spike within years or decades rather than millennia. Feathers add another layer, fluffed for insulation when temperatures drop at night, sleeked flat against the body when heat needs to dissipate. But even these advantages have a ceiling. and the peak of the PETM pushes past it in the tropics. The equatorial regions become genuinely uninhabitable, not just uncomfortable, and the animals that survive are the ones that can move. The Paleocene-Eocene thermal maximum killed nothing cleanly. It reshuffled. In our timeline, it reshuffled in favor of early primates who appear in the fossil record precisely at this boundary. Their small bodies and fast metabolisms better suited to the disrupted tropics than larger mammals. In the dinosaur timeline, the reshuffling would have gone differently. Large dinosaurs were almost certainly gigantotherms. Their sheer body mass created thermal inertia, meaning they absorbed heat slowly and released it slowly, buffering them against the rapid temperature swings that stress smaller, faster metabolizing animals. Feathers added another layer, fluffed for insulation in cool nights, sleeked against the body to dissipate heat when temperatures spiked. The tropics may have become genuinely uninhabitable, even for dinosaurs during peak PETM warming, forcing migrations toward the poles. But the poles were no longer cold. They were lush, warm, and newly opened. The heat spike that reshaped mammalian evolution would have done the same to dinosaurs, pushing diversity toward the high latitudes, opening new ecological space, accelerating specialization. The dinosaurs would have come through the PETM, changed, not broken. Quick pause. If this is working for you, leave a like before you drift off completely. Back to 66 million years ago, the dinosaurs come through the heat spike, changed but intact. For millions of years afterward, the planet continues warming, the polar forests thrive, and the dinosaur lineages spread into newly opened territory across the high latitudes. Then, about 34 million years ago, something happens that no amount of feathers or thermal mass can stop. Something geological, slow, and irreversible. The world begins to cool. The forests begin to shrink. And for the first time in the entire history of the dinosaurs, the landscape opens up, and open ground changes the rules of survival completely. Around 34 million years ago, something shifts. South America and Antarctica, which had been connected, finally separate. And the gap between them allows a current to form that circles Antarctica continuously, cutting it off from the warm tropical water that had kept it habitable. Ice sheets form for the first time in hundreds of millions of years. Global temperatures drop several degrees. The pole-to-pole forests that had defined the planet's landscape for tens of millions of years begin to shrink, pulling back from the high latitudes, thinning at the edges, leaving behind open ground, clearings, meadows, and eventually vast open landscapes with no tree cover at all. For the first time in the dinosaurs' long evolutionary history, large parts of the planet offer nowhere to hide. But open ground is not simply a different version of forest. It is a different set of rules entirely. And the first rule is that nothing large can hide. A forest predator's entire strategy depends on cover, the ability to close distance to prey without being detected, to deliver one decisive attack before the prey can react. Strip the cover away and the strategy fails, not occasionally but every time, because prey animals on open ground can see a predator from a kilometer away and simply leave. But the prey animals face the same problem in reverse. Nowhere to disappear when the predator comes. The answer, in both cases, is the same one that open plain ecosystems have produced independently on every continent in our timeline. Herd size, running speed, and the specific vigilance that comes from having hundreds of eyes scanning the horizon simultaneously. The dinosaurs arriving into open landscapes would have faced the same mathematics, and the mathematics produced the same answers regardless of what kind of animal is doing them. When Antarctica separated from South America and the Antarctic circumpolar current locked in, the planet cooled in a way it hadn't in hundreds of millions of years. Forests retreated, clearings appeared. Grasslands began their slow conquest of the continental interiors. For the first time in the dinosaurs' evolutionary history, large areas of the planet offered no cover, no tree line to disappear into, no dense canopy to break up sightlines. This is the moment that changes everything for the large theropods. An ambush predator that cannot ambush faces an existential problem. Its prey sees it coming. The same ecological logic that transformed ancestral horses into long-legged, fast-running, open plains animals would now act on every dinosaur lineage exposed to open landscapes. The ornithomimosaurs, already long-legged, light-built, fast, were pre-adapted for exactly this. The ceratopsians, already herd animals with horn defenses, would have refined those defenses for predators that now hunted cooperatively in the open. Every pressure the open plains placed on African savanna megafauna, it would have placed on the dinosaurs of the cooling Eocene. And the dinosaurs had 10 million years of warming world diversity to draw the raw material from. The open plains have already forced the dinosaurs to run faster, herd tighter, see farther. The world 23 million years ago looks nothing like the Cretaceous. Vast grasslands spreading across the continental interiors, a new kind of landscape that no large animal has ever had to navigate before. And grass, it turns out, is not simply a different plant, it is a trap. One that rewrites the teeth of every animal that tries to eat it consistently. And the dinosaurs moving into these grasslands are about to find out why. About 23 million years ago, a plant that had existed for tens of millions of years in relative obscurity begins its conquest of the continents. Grass is not spectacular. It is not tall, not colorful, produces nothing an animal would travel far to eat. What it is nearly indestructible. It grows from its base rather than its tips, meaning grazing removes the old material and triggers new growth, and fire that kills a forest clears the way for grass to return within a season. By the early Miocene, grasses are spreading across every continent that has open ground, and any large herbivore that wants to eat consistently in the new open landscapes has to eat grass. But grass is not simply food, it is a trap with a delayed trigger. Silica phytoliths, microscopic glass particles embedded in every blade, are invisible, tasteless, and slowly catastrophic to any tooth not specifically evolved to handle them. A large herbivore eating grass daily grinds those particles against its teeth for decades, and unless those teeth can either grow continuously or replace themselves continuously, the animal eventually loses the ability to chew and starves on a plain covered in food. In our timeline, this pressure rewrote the teeth of every major grassland herbivore. Horses developed hypsodont molars that grow continuously from the root, allowing decades of abrasion without wearing down to the gum line. But the ceratopsians were not starting from zero. Hadrosaurs had already evolved dental batteries, hundreds of interlocking teeth replacing themselves in a continuous conveyor, the most sophisticated plant processing system any dinosaur ever built. The direction of travel was already established. Grass simply accelerates it. Grass contains silica phytoliths, microscopic shards of glass embedded in every blade, designed by evolution to destroy the teeth of anything that tries to eat it consistently. In our timeline, this drove horses to evolve hypsodont teeth, high-crowned, continuously growing molars that could absorb decades of abrasion. The same pressure, applied to ceratopsian lineages over millions of years, would have selected for exactly the same solution. Hadrosaurs already showed the direction with their dental batteries of hundreds of interlocking, constantly replaced teeth, the most sophisticated plant processing system any dinosaur ever evolved. A late Miocene ceratopsian descendant would be almost unrecognizable to a paleontologist studying Triceratops. Lower skull to reach ground-level grass, a wider, squared-off beak for cropping rather than shearing, smaller frill because open plain herding animals advertise differently than forest animals, and teeth that grow continuously to compensate for the silica grinding them down. This is not speculation about what could happen. It is a direct application of what demonstrably does happen when large herbivores meet grasslands. The outcome in the dinosaur timeline would have been parallel evolution producing parallel solutions, because the physics of eating glass-laced grass don't change based on who is eating it. The herbivores are adapting to grass, to open plains, to life in massive herds with no cover. But what about the predators? Because the problem facing a tyrannosaur descendant on an open plain is not just one of speed, it is a problem of mathematics, and the solution that mathematics eventually forces on every apex predator that has ever tried to hunt large herd animals in open terrain is one of the most consequential developments in this entire alternate timeline. What tyrannosaurs become on the Miocene plains is not a bigger, faster version of what they were. It is something categorically different. T-Rex was not built for open plains. A 9,000 kilogram animal designed around ambush, forward-facing eyes for depth perception in dense forest, a massive skull for one decisive bite. Short legs relative to body size for explosive acceleration rather than sustained speed is a perfect forest predator and a visible, lumbering problem on open ground where prey can spot it from kilometers away and simply walk in the other direction. The open landscapes of the Miocene don't appear overnight. They expand over millions of years, and as they do, the selection pressure on every large theropod shifts in the same direction. Lighter, faster, more horizontal, legs longer relative to body. But slimmer and faster does not solve the fundamental problem of hunting large herd animals on open ground. A single predator, regardless of how fast, how lean, or how precisely evolved, faces an arithmetic problem when it approaches a herd of several hundred armored ceratopsians. The herd's collective vigilance detects the threat early. The animals on the outside form a defensive perimeter, and the predator has no angle of approach that doesn't put it against a wall of horns and mass that outweighs it by orders of magnitude. Speed only matters if the predator can isolate one animal from the group, and isolation requires either confusion or coordination. One predator cannot create confusion in a herd that large, but multiple predators working from different directions simultaneously can, because the herd cannot orient its defenses toward multiple threats at once without breaking formation. And a broken formation creates the gap that a single predator never could. A 9,000 kilogram ambush predator is perfectly designed for forest ecosystems and nearly useless on open plains. And over millions of years, the open plains would have made this fact undeniable through selection. The tyrannosaur lineage in the Miocene would have faced consistent pressure toward leaner, faster animals. Longer legs, more horizontal posture, smaller skull relative to body size, because the animals being selected against were the ones too slow and too heavy to catch prey that could now see them from kilometers away. But even a slimmed tyrannosaur faces the fundamental mathematics of large herd animal defense. A single predator, however fast, cannot separate one animal from hundreds. Wolves solved this. Lions solved this. Wild dogs solved this. In each case, the solution was cooperation, coordinated flanking, division of roles, shared pursuit. Miocene tyrannosaur descendants, facing the same mathematical problem, would have been under the same selection pressure toward cooperative behavior. A pack of 6 animals, each weighing 3 tons, working in coordinated strikes from multiple angles, is not a larger version of a single tyrannosaur. It is a categorically different predator, one that the ceratopsian herds would have had to develop entirely different defenses against. The predators are cooperating. The herbivores are adapting. The ecosystems of the alternate Miocene are settling into something that looks, in its ecological logic, surprisingly familiar, even if the animals filling every role are unrecognizable. But now comes the question that sits at the center of this entire thought experiment, the one that paleontologist Dale Russell first put into words in 1982, and that no one has fully resolved since. In 66 million years of uninterrupted evolution, could the dinosaurs have produced something that thinks? And if they could, would it think like us? In 1982, a paleontologist named Dale Russell looked at a small Cretaceous theropod called Troodon, roughly 2 meters long, bipedal with an unusually large brain relative to its body size, and asked a question that the scientific community has been arguing about ever since. He constructed a hypothetical descendant, upright, large-brained, with manipulative hands, an animal that had followed the same trajectory that primate evolution followed in our world. The model was widely criticized, but the question underneath it was legitimate because Troodon was not a marginal case. It had the highest encephalization quotient of any known dinosaur genus, and it was alive and apparently thriving at the moment the asteroid arrived. But the troodontid brain-to-body ratio, while the highest of any known dinosaur, was not yet close to the ratios seen in crows, parrots, or great apes. The question is not where it started. It is whether 66 million years of selection pressure, applied to an already above-average starting point, could have closed that gap. Crows achieved great ape equivalent encephalization in roughly the same time span we are imagining for alternate troodontids, starting from ancestors no smarter than any other bird. But crows achieved it in a specific context: social competition. Tool use rewarded by food access. The particular feedback loop where smarter individuals out-reproduce less smart individuals by enough margin that intelligence compounds across generations. The troodontids, hunting in coordinated packs, using deception and flanking maneuvers, would have been inside exactly that feedback loop. And 66 million years is a long time for compounding to work. Crows evolved brain-to-body ratios comparable to great apes in roughly 66 million years, the same span of time we are imagining for alternate troodontid evolution. This is not a coincidence to wave away. It is a data point about how fast intelligence can develop when the ecological conditions favor it. The troodontids already had the highest encephalization quotient of any known dinosaur genus, already showed evidence of coordinated hunting, already had forward-facing eyes and 3 dexterous fingers. The question is not whether their descendants could have become more intelligent. They almost certainly would have, because intelligence compounds. Smarter animals survive better, leave more offspring, and the offspring inherit both the genes and, crucially, the learned behaviors. The question is whether they would have reached human-level consciousness, and the honest answer is probably not, and not because dinosaurs were incapable, but because human consciousness is not a destination. It is a specific outcome of a specific sequence: primate ancestry, bipedalism, African savannas, the particular social feedback loops of early Homo. None of that sequence exists in the dinosaur timeline. What the troodontids could have produced is a creature that solves problems, uses tools, communicates in complex calls, hunts with deception, a creature that thinks. Whether it would also wonder why it thinks is a different question entirely, and the evidence suggests the answer is no. The question of intelligence has no clean answer. What we can say is that 66 million years of evolution applied to the troodontid lineage would have produced something significantly smarter than a Cretaceous troodon, and something that, in all likelihood, stopped well short of human consciousness. But intelligence is not the only thing the alternate timeline still needs to test. About 2.5 million years ago, Earth enters a new phase, the Ice Ages, and what the glacial cycles do to every large animal caught in their path is the final and most brutal exam the alternate dinosaurs would have faced. Around 2.5 million years ago, Earth's climate enters a new phase, one driven not by volcanic carbon or ocean circulation changes, but by the slow wobble and tilt of Earth's orbit. Small variations in the planet's relationship to the Sun that compound over thousands of years into massive glacial cycles. Ice sheets advance south from the Arctic, covering continents, locking water into glaciers and dropping sea levels by over 100 meters, turning temperate forests into tundra and tundra into ice. Then, roughly every 100,000 years, the cycle reverses. The ice retreats, ecosystems rebuild, species that survived migrate back into newly opened territory. 20 of these cycles play out over 2 million years. But cold is a specific problem, and the dinosaurs arriving into Pleistocene conditions would not have been the animals that left the Cretaceous. 63 million years of evolution separate the late Cretaceous theropod from its Pleistocene descendant. 63 million years of selection pressure that had already pushed lineages toward feathered insulation, fat storage, and cooperative behavior in the cooling Eocene and the open plain Miocene. The question of whether dinosaurs could survive the Pleistocene is not really a question about the Pleistocene. It is a question about whether the animals that the prior 63 million years produced would be equipped for it. But there is one variable the Ice Ages introduce that no previous pressure had at this scale: the 100,000-year cycle of complete ecosystem collapse and rebuild, repeated 20 times, each cycle killing the slow adapters and moving the survivors to new territory. 20 glacial cycles over 2 million years, each one advancing ice sheets across continents and then retreating, reshaping ecosystems each time. This is what the Pleistocene did to life on Earth. In our timeline, it produced woolly mammoths, woolly rhinos, cave lions, existing lineages pushed by cold selection pressure toward insulation, fat storage, and seasonal migration. The Ice Ages do not care what lineage they act on. They apply the same pressure to any large animal in the affected latitudes, and the pressure produces predictable results. A Pleistocene ceratopsian descendant would carry the marks of 2 million years of cold selection. barrel-shaped to minimize surface area relative to volume. Layers of feathery insulation dense enough to trap heat against a body that produces it. Fat reserves accumulated during summer abundance to burn through winter scarcity. It would migrate, not because migration is uniquely mammalian, but because following seasonal vegetation across continents is the only strategy that works when your food source moves. The ice ages would not have ended the dinosaurs. They never end anything that can adapt fast enough, and 165 million years of evolutionary history suggests the dinosaurs were very good at adapting fast enough. The ice ages end. The glaciers retreat for the last time. The ecosystems rebuild, and the world settles into the climate that we would recognize as our own present. The same sun, the same orbital rhythms, the same basic planetary chemistry. But everything alive on that planet, in the oceans, across the continents, in the skies overhead, is the product of 66 million uninterrupted years of dinosaur evolution. What does that world actually look like? Not in general terms, but specifically continent by continent, ecosystem by ecosystem, ocean by ocean. If you could stand in the alternate present, the one where the Chicxulub impactor arrived 10 minutes off schedule and skipped over the shallow coastal shelf, the map beneath your feet would look familiar. The continents are in the same positions. The Atlantic is the same width. The Himalayas are still rising. Continental drift operates on timescales that make 66 million years a relatively minor episode, and the geography of the planet hasn't changed enough to be unrecognizable. Everything living on that geography is unrecognizable. But the ecosystems on that familiar map are unrecognizable, and the differences run deeper than simply swapping which animals fill which roles. The oceans are the most dramatic departure from anything we know. Mosasaurs and plesiosaurs, the marine reptiles that in our timeline went extinct alongside the dinosaurs, spent 66 million years diversifying into niches that whales, dolphins, and seals would eventually claim in our world. But mosasaurs breathe air, which limits dive depth and constrains where they can hunt. The deep ocean, below the range of air-breathing surface hunters, remains a different kind of frontier in the dinosaur timeline. One that the alternate world's equivalent of whales never fully colonized. No humans means no agriculture, which means no species extinctions driven by habitat conversion, and therefore megafauna densities that no human alive today has ever seen on any continent. The continents are identical. Continental drift operates on timescales that make 66 million years a minor episode, so the geography of the alternate present looks like a map you would recognize. Everything living on that map is different. African savannas carry ceratopsian herds in place of wildebeest, theropod packs in place of lion prides, and pterosaurs circling thermals in place of vultures. The ecological roles identical, the animals filling them utterly unlike anything in our world. The oceans are the most dramatic departure. No whales, no dolphins, no seals. Mosasaurs and plesiosaurs spent 66 million years diversifying into every marine niche those groups would have eventually claimed, producing filter feeders the size of blue whales, deep diving lineages, coastal fish hunters. Australia, isolated after separating from Antarctica around 45 million years ago, would have produced dinosaur radiations as improbable and specific as the platypus and kangaroo. Animals that exist nowhere else on Earth and look like nothing else on Earth. No humans, no cities, no roads, No agriculture, no fossil fuels combusted, no species driven to extinction by a single other species expansion. Biodiversity significantly higher, megafauna continuous across continental ranges, a planet running on orbital mechanics and volcanism rather than industrial chemistry. There is one question left about the alternate present, and it is the one that tends to get overlooked in every version of this thought experiment. We have followed the dinosaurs through the heat, the cooling, the grasslands, the ice ages, and into the modern world. But the mammals were always there too, quietly, nocturnally in the margins. And 66 million years is a long time to survive in the margins. What do they become? And is there any version of this timeline in which the thing listening to this documentary could have existed anyway? Mammals in the alternate timeline do not go extinct. That part needs to be said clearly, because it is sometimes assumed that a world dominated by dinosaurs is a world where mammals disappear. They don't. Small, nocturnal, adaptable animals with fast reproductive rates have been surviving in the presence of large predators for 150 million years by the time the asteroid almost hits. And nothing about the continued existence of those predators changes the fundamental calculus that keeps small prey animals alive. What changes is the ceiling, how large mammals can grow, how much ecological territory they can claim, how far out of the margins they can move. But the ceiling is the entire story of what mammals become in the alternate timeline, because the ceiling is what determines whether a lineage ever faces the specific pressures that produce large brains. Small nocturnal animals do not need to outthink apex predators. They need to hide from them. The intelligence that develops in that context is the intelligence of concealment, of staying still, of detecting threat early and disappearing before it arrives. It is not the intelligence that builds tools or that develops the social complexity required for language, or that eventually sits upright on an African savanna and begins asking questions about the rocks falling from the sky. But the treetops offer something slightly different. Primate-like mammals with grasping hands and forward-facing eyes, the basic hardware that in our timeline eventually produced human cognition. The hardware is there. What is missing is the pressure that forces it to develop, the moment when the trees are no longer safe enough and the ground becomes necessary. Mammals survive. This is the part of the alternate timeline that is least dramatic and most certain. Small, adaptable, nocturnal animals with fast reproductive rates do not go extinct because the large predators above them are reptilian rather than mammalian. They survive exactly as they had survived for 150 million years already, in the margins, in the dark, in the underground, in the gaps. The night belongs to them completely, because the evidence from modern birds, which are dinosaurs, strongly suggests diurnal activity patterns in most lineages. A world where dinosaurs never died is a world where mammals own every hour between dusk and dawn, without competition from the apex predators. The underground is entirely theirs. Burrowing networks running beneath the feet of ceratopsian herds, hidden ecosystems of small insectivores and seed-eaters, and root grazers, living full lives in a world the surface animals would never access. The treetops hold primate-like mammals with grasping hands and forward-facing eyes, but they never come down, because the ground offers them nothing except predation. The pressure that brought early hominids onto the African savanna, the pressure that eventually produced human intelligence, never exists. The mammals live, thrive, diversify, and remain exactly what they have always been. The mammals never leave the margins. The dinosaurs never stop evolving. The alternate Earth runs its course. Brutal, indifferent, alive in ways our world no longer is. And here, at the end of this timeline, is the thought that makes the whole exercise strange in a way that is worth sitting with before sleep. The only reason any of this can be imagined is that none of it happened. You are the proof that the asteroid landed, the imagination tracing this alternate world, the mind holding 66 million years of hypothetical evolution, the particular kind of wistfulness that comes from picturing a world you can never visit. All of it exists only because the dinosaurs died. Here is the fact that the entire alternate timeline rests on, the one that only becomes strange when you sit with it long enough. The only reason you can imagine a world where dinosaurs survived is that they didn't. The mental capacity required to construct this alternate Earth, to hold 66 million years of hypothetical evolution in mind, to ask what a tyrannosaur descendant looks like in the Miocene, to feel the specific kind of wistfulness that comes from imagining a world you can never visit. That capacity exists because a rock hit shallow water instead of deep ocean. And the resulting extinction eventually produced, through a very long and contingent chain of events, a primate brain capable of wondering about its own origins. But the chain of events that produced that primate brain is not a straight line from small nocturnal mammal to conscious observer. It runs through the African savanna, through bipedalism forced by a specific climate shift that opened grasslands in East Africa around 2.5 million years ago, through the particular social structures of early Homo that created feedback loops between language, cooperation, and brain size. None of those steps exist in the dinosaur timeline. The savanna pressure never arrives because the mammals never come down from the trees, because the ground is never safe enough, because the ceratopsian herds and theropod packs that cover the open plains make terrestrial life for a small mammal a brief and terminal experiment. Therefore, the alternate Earth has no one to name it, no one to measure it, no one to find the bones in the rock and deduce what walked there 66 million years before. The alternate Earth is not a lesser world. It is a world without anyone to call it magnificent, and that is the specific thing it lacks. No one names the eras. No one finds the fossils, classifies the species, builds the telescopes pointed at the same stars overhead. The troodontid descendants solve problems, use tools, coordinate hunts. But the loop that produces consciousness capable of asking, "What is consciousness?" requires a very specific set of ingredients that the dinosaur timeline never assembles. What that world has instead is something our world has largely destroyed. Continuous megafauna across continental ranges, ocean ecosystems untouched by industrial fishing, atmospheric chemistry governed by volcanism and orbital mechanics rather than combustion. It is not a paradise. It is brutal. It is indifferent. Predators are dying, and prey is dying, and parasites are consuming both. But the dying is proportionate, ecological, cycling back into the system that produced it. The dinosaurs did not choose to rule the Earth. They evolved to fit conditions they found and kept evolving as those conditions changed, and a rock from space ended a reign that had no biological reason to stop. In the other timeline, the rock missed. Something is sleeping tonight in a nest somewhere on that Earth, its breath slowing, its brain cycling through whatever a non-conscious mind cycles through in sleep, not dreaming of meaning, not wondering about purpose, not aware that somewhere in a parallel timeline, The only creatures who ever asked, "What if?" are asking it about them. There is another question hiding inside this one. We answered what the dinosaurs would have become. But there is a parallel story about the mammals that stayed small, the oceans that never knew whales, the night sky that was watched by no one. That deserves its own hour. If you want that story next, subscribe. That is the only way to know when it arrives.